All right, all is well that ends well, and today we end with Helton-Howe trace, content character, and quantization. And because I do not dare to mispronounce the speaker's name, let me just play it.
Xiang, Tang.
It's all yours. Take it away.
Thank you very much. So I would like to start my talk by thanking the organizers for the invitation and the opportunity to speak in this very interesting conference. So today I'm going to talk about the Helton-Howe trace and the Connes-Chern character. So Helton-Howe trace was studied by Helton and Howe in the early 70s in their study of almost commuting operators. And their trace formula was greatly generalized by Alan Kong using the cyclic theory and the Chern character. So what I'm trying to explain to you today is, these are the classical objects in the pointer. So these are the classical objects in non-commutative geometry. So my hope is to explain to you, we can try to put these classical objects into a family. And if we have maybe one single object, it's hard to study it. But if we put them into a family, then maybe we'll have a better chance to understand the geometry and maybe to detect more information from this classical object. Okay, so let's start. So here's the summary of my talk. So we will focus on the study of this family called maybe I just point, the weighted programming spaces. So if you are not familiar with it, don't worry, I'll explain to you what they are in a moment. And we'll try to relate this family to something called turbulence quantization. Some parameter t will appear again. So here's the outline of my talk. The first part, I will try to recall the history, the turbulence operators and Helton-Howe trace formula. And the second part, I will try to bring in Kong's great discovery of cyclic theory and the Chern character. And then in the last part, I hope to explain to you some of the results we have obtained in this project. So this talk is based on joint work with Yi Wang and Dechao Zheng. So with slides, I can show you their pictures. So here they are. So this is Yi Wang. She's now based in Chongqing University in China. So Dechao Zheng is in Vanderbilt University at Nashville. So let's start from the first part, the Helton-Howe trace formula. Okay. So here we study, the simplest possible topological space, the unit disk inside the complex plane. Right? Right. And on this space, we have the L2 space. Right? We all learned this in our first analysis class. And then we have a nice subspace, the space of L2 analytic functions. This is a closed subspace of L2 space, right? So that's the projection, the orthogonal projection is what we usually call the Ziegler projector. And the L2 space of holomorphic functions are called the Bergman space. So now using this orthogonal projection, actually it showed up today in the previous talks, we can have this turbulence operators. It's the contraction of multiplication onto our Bergman space, the subspace. And this is a classical result when we compute the commutator of the turbulence operators is actually a compact operator. Okay, so this led us to the great discovery of K-homology and extension theory. So let's briefly recall it. So we have here the compact operator algebra, and then we have the system algebra generated by the turbulence operator and compact operators. And we have this function algebra and the short exact sequence of system algebras. Right? That's what we all learned in the extension theory in the 70s by BDF. And here, that's the probably one of the very first index theorem we know from the Winding number theorem, right? Even pre-RTR single. So what we are trying to study today is we would like to go beyond the K theory. We would like to detect hopefully more refined information beyond K theory and K homology pair. So to do that, here is another nice observation. So just now we said the commutator between Tobolitz operators is compact, but actually when we consider here, oh, sorry, I moved back. And what do we have is if we consider the commutator between TZ and TZ star, it's not just a compact, actually it is much nicer compact operators, it's trace class operators. We can compute its trace, right? And actually this property extends to all smooth functions. And that's the kind of trace class operator property. Now with this, we can ask the trace, to compute the trace, right? So in finite dimensional case, we know if I have two matrices, the commutator has vanishing trace. But now these are not finite dimensional vector space anymore, so the trace does not automatically vanish. Actually, this is a nice formula proved by Helton and Howe in the 70s. The trace of the commutator of the Tobolitz operators is actually having a nice topological expression. Yeah, please.
That formula, if you look instead of the Lebesgue measure on the disk, you look at the Lebesgue measure on the circle. Anything else?
Very good question. Actually, I'll come to that in a moment. Yeah, thank you, Grace. Yeah. So here, just one remark. So here, although we write this as an integral over the disk, but by the Stokes theorem, right? So we can do the integral over the interior, but we can also, if we require our function to be continuous up to the boundary, it's actually an integral or some formula on the boundaries. So it's really about the topology on the boundary too. So it's, and this kind of formula was, studied in the 70s. Many people were involved in the study, Helton-Howe and Carey Pincus, Brown, many people, I guess, were involved in such studies. So what we're trying to study today is trying to look at generalizations of this trace formula. So first of all, as I said, I would like to put this space into a family. So I would like to introduce this parameter T. So in this, study of Bergman spaces in harmonic analysis, there's a natural family of Lebesgue measures or generalizations of measures to consider on the disk. So here you can see that dx dy is the Lebesgue measure on the disk. But now we are introducing this 1 minus z squared. That's basically the distance function to the boundary, because our function, this function vanishing at the unit circle. So I'm introducing this weight, and this is the weight. People in harmonic analysis actually are interested in such a weight. And now with this weight, we can ask the same type of Tobolitz operators on the weighted Bergman space, the L2 space and L2 analytic functions. Okay. So now I guess the natural question is, okay, we can talk about the Tobolitz operator in the same sense. Everything just, putting T in the proper place. So the question is, okay, so how about the commutator? So you can check, well, with a little bit. So before the check was, we write down the orthonormal basis on the Bergman space. Now, with the T, still we have this orthogonal basis by monomials, but we have a weight. So it's a weighted shift. So you can still compute. It is a trace class operator for commutators. So this is a nice calculation to do with. Then the question is, since the commutator is a trace, how about the trace formula? Does it depend on T, or this is constant with respect to T? Right? So I guess, go back to the question we started with. If we look at the pairing of the trace on the K-theory elements, Then, because this is a, rigid object, right? K-theory of extension class are just integers. Now we have a family, so they shouldn't be changing the K-homology class. And this number does not change. So this tells us, our question here is not just on the pairing between trace with extension class or the secondary co-cycle with K-homology class. We're trying to ask what happens for this maybe Connes-Chern level. Does it change, or what information do we get if they change? Okay, so that's the kind of a question on the unit disk, the trace form. Okay, so such a study actually was extended to the boards in the 70s too by Helton-Howe. So just now you can think about, we have a pair of operators. When we have high dimensions, we're going to have many operators to get involved. So that's the geometry we need to work with. We have Cn and then the unit ball inside the Cn. Okay. So now on this space, we can have this family of Lebesgue measures with the weights. So you can see that this function, again, shows up. So this is the same function. Now with this one, we can talk about, again, everything like what we had before. The L2 space, L2 holomorphic function space. Right? And then we have the Zego projection and the turbulence operators. So now we go from the disk to the ball, high dimension. So everything is a natural generalization. So now we can ask the same question, right? So about the commutator. But now there's a slight dichotomy. The dichotomy here is for n dimension, for the disk, n is equal to 1, the commutator is a trace. But now for higher dimensions, the commutator is not the trace anymore. Actually, it's not the Helton n class. N is not dimension. We need to require this p greater than n. Or this is in the kind of the m plus ideal. If you are familiar with what I mean, the m plus ideals. Okay. So that's the slight difference. But now the nice formula is, although the commutator has this weakened property, but if we do the full antisymmetrization, this is the discovery of Helton-Howe. Actually, this is still a trace class operator. So there's a non-trivial cancellation about singularities. And then for this full antisymmetrization, so it is actually a trace class operator. So there, during the Helton-Howe time, they were only interested in the t equal to 0 case. But they proved the following nice generalization of the Helton-Howe trace formula. You can see that it's just, before we had 2 copy, but now we have 2 1 copy. Okay, so that's the development in the, I think, the early 70s. Okay. Now, what we are trying to discuss the next is we would like to bring in, the great contribution from Alan Kang on non-commutative geometry and cyclic theory to study this kind of trace formula. So the construction we are discussing today is from this reference, this IHES publication, this long article. Right? So to do that, we need to probably introduce some homologic algebra to put our study into the right framework, the cyclic theory. So I will spend the next few slides about that. So to do that, we will start with a Fréchet algebra, so some algebra with topology. Okay, and then on this algebra, we'll consider some co-chains. So basically, we're looking at multilinear functionals on the algebra. That's what we are looking at. So you can think, we are looking at the generalizations of traces. The trace is just a linear functional, but now we have a multilinear functionals. And on this space of co-chains here, so these are the co-chains, we have this differential. That's the differential introduced by Hochschild in the 50s. So in his study of deformation of algebra. So that's the Hochschild differential, and then you can check this does form a chain complex. So we have a cohomology, that's the Hochschild cohomology. Okay. So that's about the Hochschild, and then the great discovery by Alan Connes is, we can, introduce a very tiny restriction about the co-chains, and then it led us to more important topological information. So that's the second cohomology. So we impose this condition on the cyclic permutations of the co-chains. So this, if you look at the trace, we know trace of AB is equal to trace of BA, right? So this is like the permutation property. Now we generalize it. Then we have this kind of a cyclic permutation property. So it's not a long computation to check is, well, such a subspace of co-chains satisfy this cyclic permutation property still is invariant under the differential we just had. So the cohomology of this complex is historically using the C lambda complex, and the cohomology is the cyclic cohomology of the algebra. So this example is to, I hope to convince you this is a right object to work with. So Hochschild, Klose, and Rosenberg was all about Hochschild cohomology. Alan Connes is to talk about the cyclic cohomology and also the Fréchet algebra version of the computation. So you can see that the Hochschild cohomology of so M here is the smooth manifold. And the algebra C infinity means the algebra of smooth functions on a smooth manifold. Okay, so then we compute the Hochschild cohomology. It's basically the de Rham currents. Okay, so they are kind of a dual of the differential forms. And so here I have, kind of cheated a bit. So this is the stabilization of this object, the periodic cyclic cohomology. When we do the stabilization, then we don't look, we see those kind of closed forms or closed currents anymore. So these are just the usual de Rham homology of the manifold. So you can see that the cyclic cohomology provides us the right topological information, de Rham theory, for the non-commutative geometry. Okay. So that's this comment. And furthermore, we know the cyclic cohomology pairs naturally with the K theory of the algebra. That's the important ingredient for the non-commutative geometry, for the Poincare duality, or the pairing between homology and cohomology. So now let's get back to the study of the Bergman space and the Helton-Howe trace. Okay, so to do that, we look at this Connes generalization of the chain character for the p-summable Helton-Howe modules. So the kind of a building block is this kind of a semi-commutator. So we look at the composition of operators. Okay, so if T is a homomorphism, then this one vanish. But in general, we know T is not a homomorphism, so this is a non-trivial quantity to start with. And then this is the formula Alan Connes introduced as the chain character associated to a p-summable Helton-Howe module. So here we need to require, the semi-commutator to have Sheldon P properties. Okay. With that, we can insert enough number of the semi-commutators to make sure that this is a trace class operator, so the trace is well defined. And then all the numbers and even homotopy property can be developed under those restrictions. Okay, so that's for the Connes chain character formula for p-summable Helton-Howe modules. So I guess here just I cite Alan Connes' result. This formula we just introduced, is actually a cyclic cocycle. Satisfy all the properties we introduced. It is cyclic with respect to permutation, and it is the co-cycle. And actually how this is related to the Helton-Howe formula is, well, you can look at the Helton-Howe co-cycle by the computation. It's actually a co-cycle on the sphere. Okay. So that's the relation, also examples of cyclic cohomology. Okay, great. So that's about the introduction of cyclic cohomology. And now let me come to the questions we would like to discuss in today's talk. So I would like to ask the following question. So if we have this Helton-Howe trace for the anti-symmetrization of n Tobolitz operators on the n-dimensional balls, complex n-dimensional balls, does this depend on the T? Okay. So, well, the next question is, how about if we look at the Chern character? Does this one depend on T? So we know at the K-theory pairing level, they do not depend on T. Okay. So that's the the question we would like to answer. So any questions about the, yeah, please. Yes. Right, so T could be greater than or equal to -1. When T is equal to -1, that's what Chris was asking, the whole theory for the Hardy space on the circle. Yeah, T is always greater than or equal to -1. Yeah. So in operator theory, they can make T less than -1, but then the geometry is missing. Great, so let's continue our discussion. So you can see that to answer the questions we just asked, we need to start with looking at the building block in Connes-Chern character, this semi-complicated. So this is actually, for people who are familiar with quantization, this is like the quantization asymptotic expansion formula, the kind of the first term. So actually, this is related to quantization. So we can view this T map, the map from functions on the ball to operators on this family of Hilbert space parameterized by T. And actually, in the Tobolitz quantization theory, so you can think about this T actually is related to 1 over h bar. And when T goes to infinity, you think about h goes to 0. Okay, so this kind of operator expansion formula was well studied in the literature, going back to, I guess, Boudet de Monvel and many people contributed to this kind of asymptotic expansion, but certainly Boudet de Monvel is one of the important names in this study, but also like Eckhart was involved in this too. So here the study was about the operator norm. So we look at the asymptotic expansion with respect to T up to Tth power. So you can see that the T is proportional to 1 over h bar. So when we have 1 over T, the negative power is actually expansion for h bar power. So that's the historical study. So I will not go through this, very carefully. So just to tell you the first term in this asymptotic expansion is like this nice, symplectic or Poisson structure associated to the ball with boundary. You can also say this is kind of the symplectic or Kähler form associated to the Bergman metric on the ball. So that's the historical study. So now you can see that we are studying the trace properties. So we need to kind of enhance the study here to the trace norms. That's what we are discussing in the next couple of slides. Okay. So yeah, here I mentioned this is a well-studied subject in the literature in the name of Tobolitz quantization or Berezin Tobolitz quantization. Okay. both in mathematics and also physics community. So let's move on. So what we are discussing is, so we need to have this study the asymptotic expansion property for Sheldon P norms. So now, so here is the result we have. So we are studying the asymptotic expansion again to this, tth power, or 1 over tth power. That's this kind of this part. So you can see that here we want to go to kth power expansion. So we need to require f and g to be k plus 1 differentiable. So for our later formula, we only need to ask for the k to be 1 because we only need this part. Actually, the higher part, the singularity is actually nicer, so actually they disappear in the trace. So you can see here the main information I want to bring you is, you can see there's a difference between the n is greater than 1 and n is equal to 1. When n is equal to 1, the remainder term is actually already trace class operators. You can directly compute the trace. But for n is greater than 1, this is again this, n plus Sheldon P class. This is not the, the Sheldon N class. So there are more estimates, so maybe I'll just go through this very quickly. So that's about the coefficient CLT is proportional to the 1 over tth power. So this is the formula for operator norm estimates. And here you can see that for the Sheldon P norm estimate, actually we are improving a little bit for the T. Or you can say we are kind of, losing something because the decay is slower. We have a positive power here. And then again, you can see a slight difference between the Sheldon P, the n greater than or equal to 2 or n is equal to 1. Again, this subtle difference. Okay, great. So that's about the operator expansion. So now let's look at the, the example I started with, the unit disk. So now we want to look at the form. Yep. Yeah. The difference is at this range of P. Right. For n equal to 1, P is allowed to be 1. But for P greater, right, the estimate is the same. Yeah. So now let's look at the disk case. So in this case, actually we are able to prove the following trace formula for the semi-trace. Of course, this semi-trace, this is not a topological quantity, so you don't expect to have nice local formulas. So besides this, nice local integration formula, there's a long local term hidden here. You can see these are Laplace operators, but on the product of the disk. And then we have a positive function here. This one depends on T. But the nice observation here is, this one is actually symmetric with respect to f and g, right? Because there's an integral over d times d. So when we do the commutator, they vanish. That's the formula for the commutator in the one-dimension case. P sub last term P rho. Oh, this is the function. I did not tell you the formula. P. Phi. Oh, phi is the Mobius transformation. Yeah. Yeah. So that's the, the information from the n equals 1 case. You can see that in general, if we're interested in this, the semi-commutators, it does depend on T. But if we look at the commutator, then this one does not depend on T. Kind of a very interesting kind of special for the commutator, trace of commutator. And another information here is you can see, although this one depends on T, but what we can tell from studying this rho T more carefully is rho t as t goes to infinity actually die to 0, converge to 0. So this term actually, when we take a large t limit, they will drop out. So we eventually get to this kind of formula for the anti-holomorphic derivative and holomorphic derivative. So we are using this trace of a semi-commutator, we are able to see some residue of the complex geometry or complex plane information from the semi-commutator. So that's the information we don't usually see in the K-theory and the cyclical homology pair. So some kind of a more refined information is going on to study more. So that's about the one-dimension case. So any questions before I talk about the small example or application of this formula? Okay, so here, we can, sorry, I should go back. We will look at this formula. So this one actually is related, we can use it to study something called the Hankel operators. They are the kind of the sibling of the Toeplitz operator. The Toeplitz operator is the projection contraction to the Bergman space. But this one is going from the complement of the Bergman space. Okay? And this is well studied in operator theory and also harmonic analysis. Now, if we use that, we can, it's basically 1 minus the Ziegler projection, and then the semi-commutator we have actually is written as the composition of 2 Hankel operators. So now using the formula we just saw, we can try to use the formula here to study this kind of Hilbert-Schmidt law of the Hankel operators. Right? So this provides us a kind of a device to study the Hilbert-Schmidt law. Oh, sorry, I clicked the wrong button. So now, remember, just now we had the Laplace of G in the formula. But if we assume G to be subharmonic, then we know it's non-negative. Then we can naturally lead us to such a nice, estimate of the Hilbert-Schmidt law of Hankel operators from the study of the trace. So that's a kind of a byproduct. Now let's move to the high dimensions. Okay, so here that's the remark about large t limit. So when t goes to infinity, actually this term goes to 0, and then we got to this nice geometric. So about the dependence on t, and then also the remark about holomorphic structure, holomorphy of the disk. So let's move to the high dimension. So one new feature we need to pay attention is for high dimension, we need the semi-commutator is Sheldon P with the P greater than n. So if we want to come up with something trace class, we need to choose P large enough. Okay? We need to choose more than what we used to choose for the n-dimension, one-dimension case. We need to choose P greater than n pair of functions. So another feature that's what we just saw also for the one-dimensional case. We have this decay of the Shelton P law. Now combine them together, you can check that if we just, because here we choose P to be n plus 1, because of this extra kind of bigger choice of P, we cannot choose P equal to n because the semi-commutator is not n Sheldon n class, it's n plus class. So the natural integer to choose is n plus 1. Now, with this and with this estimate, well, can check that this Chern character actually converge to 0 as t go to infinity. So this is also compatible with what we just saw in the one-dimension case. The trace of the commutator also have kind of a change with respect to t, right? So here, just one example, you can see that if we don't choose p equal to n plus 1, if we only choose p equal to n, then this is not a trace class operator. So of course, there's another way to fix this. So instead of working with the classical trace, we can try to work with, the Dix-Meer trace, right? And then one can compute the trace formula here. And that's, so what we are discussing today is what stay with the usual trace and compute the trace of this operator. So that's the kind of the beginning of the observation. We see that the Chern character does depend on T. And this comes from this kind of a certain M plus property of the semi-commutator. So here is the leading term. So to tell the leading term, remember I just now discussed about the asymptotic expansion. The first term is this kind of a nice Poisson structure on the disk. And now with that, we're able to compute the asymptotic leading term for the trace of the Chern character. So just now we saw that the decay of the trace is about 1 over t. So we're computing the coefficient of this first leading term. So now you can see that for this coefficient, actually it's basically, again, the Poisson bracket. Again, this part for F1, it only depends on the holomorphic differentiation. For G, only depends on the anti-holomorphic differentiation. So again, this kind of a phenomenon of holomorphy information is included in this large T limit. So that's about the variation or the large T behavior of the Chern character. It's telling us, well, although it depends on T and vanish as T goes to 0, but the asymptotic leading term provide us with the Poisson geometry or the holomorphy information of the disk. So that's about the Connes-Chern character. So now let's try to go back to the original Helton-Howe formula, the full antisymmetrization. Okay. So to do that, here actually we look at a kind of a one step back. We are not doing full antisymmetrization, but only partial antisymmetrization. Okay. So what we did here is we still would like to kind of track the dependence on the F part and the dependence on the G part. So what we did here is, well, for the first part, we call it the antisymmetrization on the first component. So like the odd component, the one component. And then for the second type, we do the antisymmetrization on the G part. We don't change F. It turns out such an antisymmetrization is enough to get trace class. So this is kind of the, I guess, analytic improvement from the Helton-Howe observation. The full antisymmetrization is a trace class operator. So actually, it's enough to do the partial antisymmetrization. It's already a trace class operator. Okay. Now we can ask about the trace formula for this already. But the trace formula for this operator actually is very involved. This is, the example you can see is already in the case of one dimension. The trace formula is the formula I just showed you on the disk case. It contains two parts. One part is the integral, the other part is this long local formula on the double of, on the product of integrals. So we don't have a nice formula for the trace of the partial antisymmetrization on the higher dimensional balls, but we do have a formula for the large T limit. When we take T to infinity, you can see that all those long local terms, actually, they have higher power of T, so they will go to 0. And then you can see that we still get back to this kind of del F, the del bar G pattern again. So this kind of tells us something going on about this kind of a complex structure information in this large T limit. Now the next part is about how about the full antisymmetrization. It's still kind of mysterious to me, but actually the full antisymmetrization does not depend on T. is independent of T. And the formula is basically just what Helton-Howe discovered in their original paper. So what we prove was, well, we try to prove this does not depend on T, and then we use this formula to compute, to provide a kind of a different proof or independent proof of Helton-Howe's formula. So I guess one kind of a geometric explanation to me is, well, this one is actually diff invariant. So somehow it seems to suggest this one is kind of a diff invariant cocycle, and such a cocycle is kind of special.
Can you remind me why this value -1 is so special for your parameter?
So this one is related to this T. If T is less than -1, this integral will have problem. Yeah. There's regularity, the singular integrals. Okay. Any other questions? Okay, great. So let's maybe a few remarks about the proof. So the first remark is, well, here, what we are able to show is actually in the original Helton-Howe trace formula, they worked with smooth functions. But actually, in our development, it's enough to have C2 functions. So basically, in our, let me go back. So we need to look at the semi-commutator expansions. But now you can see to get to this kind of term, we only need to get to the first order expansion. For that, we need the regularity to be second differentiable. So that's why our formula works for C2 functions. So that's the first remark. And the second remark is here in our proof, actually we used crucially the symmetry on the balls. There's a non-trivial connection to representations. So they are symmetric domains. We have non-trivial symmetry on the domains, which will allow us to do the estimate at the one point and use group symmetry to push it to everywhere. Okay, so that's the remark. The Mobius transformation. So the third one here is about this connection to Heisenberg calculus with the different, so in different directions, somehow we have different weights of regularities. So we have the radial direction. So here we have the picture. So this is only kind of one dimension, but high dimension is kind of along the similar idea. Along the radial direction and the spherical direction, the regularity behave slightly differently. This is related to the Heisenberg symmetry here on the board. So that's about this one. And the last one is, well, for the trace formula, basically, the main tool we use is kind of generalization of the Cauchy integral formula. So that's about the remarks. Any questions? Now, let's move to the last piece of slides. So there are two directions we'll try to look at the moment. So the first direction is, we have looked at the balls. So a few weeks ago, the kind of mathematical physicist Connes-Chern, who is working on mathematics related to condensed matter physics, he convinced me that there is an interest to study the similar formula for the complex plane case, or even high-dimensional complex plane case, the Bargmann-Fock space. So it's the generalization of the balls using this weighted Gaussian measures. On the plane, or on the high-dimensional space. So of course, the balls are special examples of strongly pseudo-convex domains. So almost all the analysis structure, the Tobolitz operator, Ziegler projection, they are developed for the strongly pseudo-convex domains. So the same question can be asked in that generality. So that's about the one direction we are looking at, generalizations to more interesting spaces. Another direction is, but we're looking for the kind of that connection to algebraic K-theory. So classically, the Helton-Howe trace formula is related to algebraic K2. And it's related to determinant invariance on the Steinberg symbols. So now we have all this higher version, the n-tuple operators version of the Helton-Howe trace formula. So what is the right framework for the generalizations of algebraic, maybe the multiplicity of K-theory or any suggestion? Marcus? Oh, good question. That's the algebraic K2 of C infinity on the essential spectrum space. Okay, so that's the two directions we are looking at. And thank you again.